I continue to work through homework problems where there will be test problems exactly like these homework problems. And so this problem is number 2 in problem set number 8, and it gets into Archimedes' principle. And so this is a principle for whether things sink or float in other things. And so more specifically, this is a story of the buoyant force. So I'm going to write force buoyant. And before we even get into symbols, just think of this as the buoyant force, which is to say that if an object is immersed in a fluid, the buoyant force of the fluid back on that object is equal to the weight of the fluid displaced. What this means is that if the object goes into the fluid, some of the fluid displaces away to make room for the volume of the object. So for example, in this problem, if we could imagine the fluid is water, and then we've got some volume, let's say half the volume is above the water, and then the other half is below the water. For the lower half of this volume, so we could say this is V over 2 and this is V over 2. If you can imagine, originally the bottom part that you see with the dotted lines, that was originally water as well. And so for the volume of that object to submerge into the fluid, so if you can imagine, you have fluid here, you have fluid here, and originally you also had fluid where you see the submerged part. So fluid had to displace away. Fluid is surrounding the object on all sides, and there was originally fluid where the object was. And so some of the fluid, i.e., some of the water, got displaced. And so the weight of the fluid displaced is what the buoyant force is going to be. So if I draw a free body diagram where I let the center of the mass of the object have some mass, and in this case, we'll call it the mass of the block, because this is a block where half of the volume gets submerged. There's going to be some buoyant force, F, let's call it BUOY, and that force is opposed by the weight of the block. And so this is going to be the mass of the block times G. So now, what is the weight of the fluid displaced? Now be careful here. When it says the weight of the fluid displaced, it's not the weight of the object that goes into the fluid. It's the weight of the fluid that had to move away to make room for the object. So in this case, we're talking about the weight of the water that was displaced. So another way in which we can think of the weight of the fluid displaced is we can think of it as the mass of the fluid displaced times gravity. And so there's another important concept here, which is density. Density, which is often used the Greek letter rho, is defined as mass per volume, which is simply m over v. And so if density equals mass per volume, mass equals density times volume by just simply multiplying both sides by capital V. And so I can rewrite this term right here as equal to the density of the fluid displaced multiplied by the volume submerged. Okay, and so in that case, that's this part right here, okay? This lower part of the block is the volume that was submerged, but it's the density of the water, okay, that we're interested in when we think of the weight of the fluid displaced. So if we've got a sum of our forces in X equal to the buoyant force is positive, the weight on of the block due to the gravitational force towards the center of the Earth, that's downward, that's negative, so that's minus mBg. And since we don't have any acceleration in this is actually in the y direction, this is going to be equal to 0, which is to say that the force of buoyancy is equal to the mass of the block times g. But remember, I showed how the force of buoyancy could be rewritten as the density of the fluid displaced multiplied by the volume of displacement. And so in this particular case, the force of buoyancy is going to be equal to the density of water. It's going to be equal to the volume of the block that is submerged times g. This is just rho times v is a fancy way of writing m. And that is equal to the density of the block, the volume of the block, times g. This is just a fancy way of writing the mass of the block. So on the left, I have my buoyant force, which is equal to the weight of the fluid displaced, which is equal to the weight of the water displaced, which is the density of water multiplied by the volume of water displaced, which happens to be the volume of the block that is submerged. That's the mass of the fluid displaced multiplied by g. On the right, I just have the weight of the block, mbg, and I rewrite that as density of the block multiplied by volume of the block, because mass is density multiplied by volume, as I showed right here. So I can cancel out g, and that means that I can divide both sides by the volume of the block so that the density of the block is equal to the volume submerged of the block divided by the volume of the whole block multiplied by the density of water. And so in this problem, 1/2 of the block is submerged. And so that means VB over 2 divided by VB rho water. And so if you have VB over 2, that's half of the block. And then you have VB on the denominator. This term right here will be 1/2, which is to say that if half of the block is submerged in the water, precisely half of its volume is submerged in the water, then its density is precisely half of water. Turns out if, say, 1/3 of the volume of the block submerged in water, with that same mathematical formulation, you'd find that the density of the block would be 1/3 of the density of water. So the key idea is here. Buoyant force is equal to the weight of the fluid displaced. But be careful, because we're not talking about the object's weight. We're talking about when the object goes into a fluid, some of the fluid has to move to give way to make room for the object. So how much fluid got displaced, we want to figure out how much is the weight of that. We can describe weight in terms of mass times gravity, but then we have this other idea of density, which is mass divided by volume. When we do a free body diagram in the vertical direction, we find that the weight of the fluid displaced is positive, y, upward, weight of gravity, downward. And so we can say that the buoyant force is equal and opposite the weight of the object. And so the weight of the object is held up by this buoyant force. And so we can rewrite this buoyant force as the density of the fluid, in this case water, multiplied by the volume that is submerged. That's the amount of water that had to move away. That's a fancy way of writing the mass of the fluid displaced, and then the mass of the fluid displaced times g is the weight of the fluid displaced. And so similarly, we can say that the weight of the object, which the buoyant force is balancing, we can rewrite that as, if weight is mg, well, we can rewrite m as the density times the volume. So that's the density of the block times the volume of the block. We found the g's canceled. And since we have half of the block submerged, the ratio of half of the block's volume to the block's volume, we find that the density of the block, which is half submerged, has half the density of water. Now, if the block was completely submerged, let's say that it was submerged such that it just went, the very top of the block was right at the surface of the water, then the ratio would be 1 to 1. And that would be that the block would have exactly the same density as the water. So you know that if something floats in a fluid, the density of it has to be less than the density of the fluid. Right when the density of something equals the density of the fluid, the entire volume just goes below the surface. So anytime we're going to have any floating, we have to have a density where the density of the object is less than the density of the fluid. Problem number 7 deals with the concept of thermal expansion. You may have noticed if you've driven over a bridge that usually there are segments of the bridge that are separated by these metal joints. You just don't have a completely uniform slab of, say, pavement spanning the bridge. You'll have like a slab, and then you'll have a metal joint attached to another slab, attached to another metal joint. And that's to account for the fact that when temperatures change, the actual length of the pavement span of the bridge actually would stretch or contract based on if it gets heated up or cooled down. And that would not be good. So you have a little leeway by putting these joints in between the pavement slabs to account for slight lengthening or slight shortening based on whether the pavement is heated up or it's cooled down. So the basic idea is that if you can imagine the pavement, if heat goes into the pavement, you're going to have the average distance between the molecules in the pavement be a little bit greater, and you're going to have more of a volume. And similarly, if heat was lost, if it got really cold, you can imagine that the average distance between the molecules would not be as much, and it's going to begin to contract. So we have a problem where we've got an object, and the object has some initial length equal to 20.000 meters. We're told that the initial temperature is equal to 20 degrees Celsius. We're told that the final temperature is equal to 30 degrees Celsius. So we know that there is a heating up going on, which is to say that there's going to be a little bit of lengthening of the object from its original length of 20 meters. We know that because our delta T, which is going to be equal to T final minus T initial, that's equal to 30 degrees Celsius minus 20 degrees Celsius, which is equal to positive 10 degrees Celsius. The key there, positive. We have an increase, and so we're going to have a lengthening. And then we are also told that for the object's material, we have a coefficient of linear expansion of 1.2 times 10 to the minus 5, 1 over k. So, got a change in temperature. We know that there's going to be a slight change in the length of the object. So, we are going to say the change in L is equal to the coefficient of linear expansion multiplied by the original length of the object multiplied by delta T. We have all of these values. We have 1.2 times 10 to the minus 5, 1 over k. We have 20.000 meters, and we have 10 degrees Celsius, and that's positive. And so notice how you have, for the coefficient linear expansion, you have a 1 over k, and you have Celsius for the temperature. You might be like, well, how does the Celsius cancel out the Kelvin? Well, it does because they're both units of temperature. They just have different 0 points. So they very much have the same units. It's just that they have different starting points. One is shifted over from the other, if you will. And so one change in degree Kelvin is the same thing as one change in degree Celsius. More specifically, we say that if Kelvin equals 0, which is what we call absolute 0, we say that 0 degrees Kelvin is equal to negative 273.15 degrees Celsius. But again, it's just they're offset. It's not like a degree of Kelvin is any different than a degree change of Celsius. They just have a different 0 point. Now, if they had different increments, then we couldn't just cross them out. But we can cross out Kelvin and Celsius because one change in 1 degree Kelvin is the same thing as one change in 1 degree Celsius. They just have different 0 points. So if I go ahead and do the math, I get 0.00024. And so be careful, okay? This is the change in delta L. So the new L final is going to be L initial plus delta L equals 20.000 meters plus 0.00024 meters. And so, actually, I did one too many zeros there. My apologies. It should be 0.0024. And so that would be equal to 20.0024 meters. A 10-degree change in Celsius changes the length of the object by 0.0024 meters. A little background before we dig into problem number 8. I'm going to draw a little diagram here where we're going to have heat, which is often represented by Q. We're going to have that on the x-axis, and we're going to have temperature be on the y-axis. And let's take water. Water can exist in different states, and you can add heat or take away heat from water, and that can change the temperature at a given state of the water, whether it's solid, liquid, or gas. And it can also help transition from, say, solid to liquid, or liquid to gas, or gas back to liquid and liquid back to solid. So let's say that we start with water in its solid form, which we often know as ice. So imagine we had some ice and we start having heat go into the ice. All right, like imagine like we had like a blowtorch and we start hitting the ice with the blowtorch, or we take an ice cube and put it on top of a stove. Heat is going into the solid ice. And so as heat goes into the solid ice, you're going to have an increase in the temperature of the solid water, i.e. ice. The molecules of H2O are going to start moving around faster and faster because that is the definition of temperature. Temperature is the average kinetic energy of the particles of a substance. So if you can imagine the particles moving around more and more, you have a higher and higher temperature. However, you can imagine that the solid, if it has enough heat go into it, it starts to go through a phase change from solid ice to liquid water, what we know as melting. And so it turns out that when you go through a phase change, heat still gets put into the substance, but the temperature does not change because towards making the transition between states. So you see where it flattens out? That's when you're going through your melting. Once all of the water is melted and that's now in a liquid form, if we keep applying heat, so imagine we have a container, it had ice, we put it on a stove or we hit it with a blowtorch and we melted it. So now imagine we have on the stove a container, it's got water. If we keep putting heat into it now and it's all water, we're going to start to see the temperature ramp up again because now the water is going to consist of H2O particles that are moving around even more and more rapidly, higher and higher temperature. Okay. But eventually that gets to a point where the liquid starts turning into a gas. Okay. This is what we call evaporation. And so it turns out once we get to a point where all of the water is transitioning into water vapor, you're again going to get this plateau. This is not to say that we've changed the amount of heat we're putting in. We're putting heat in all the time in this graph. It's just that sometimes when you're in a particular state of a substance, you'll get the temperature to rise. But then when you go through transitions of the states, then the heat is going to the transition itself. It's going to bonds being broken or bonds being put back together. Because that's the other thing. We can go the other way. You can imagine we could start with water vapor, gas, and imagine it's losing heat, okay? And then we have the gas condensing into water. And so the temperature of the water is going down as we lose heat. But then we've got this transition from the liquid water to the solid ice. During the transition, we don't see a temperature change. But now once we're all ice, we could see more and more heat lost from the ice. So this goes each way. And just one more time, just imagine it's solid ice. Add heat, add heat, add heat. So the temperature, the average kinetic energy of the molecules of the solid ice is getting higher and higher and higher. But once there's that transition from solid to liquid, we're still adding heat, but that heat is going into the transition of the state of solid to liquid. And then once we're all liquid, now additional heat's going to raise the temperature again. It's going to raise the average kinetic energy of the water in the liquid form. But then eventually that liquid form is going to evaporate. And so that transition from the liquid water to the gaseous water, i.e. water vapor, we have a plateau. Okay. And so when we have these transitions between solid and liquid, that is often called the latent heat of fusion that is required to go between solid and liquid or liquid and solid states. And when we have this transition from liquid to gas, we often call this vaporization. Okay, and so energy required in the transition from liquid to gas or from gas to liquid. Okay, so in this particular problem, we've got a situation where there's a man. And so what I'm going to say is the mass of the human body in this particular case, because the human body is going to cool down by perspiration. Perspiration evaporates, and evaporation is a cooling process. And so the body in this problem has 67.0 kilograms of mass. So we are told that the body is going to cool down by 0.700 Celsius. And so, in other words, the change in the temperature of the body during the evaporation from the skin, i.e. perspiration evaporates, cools off the body, that's going to be T final, because the change is always the final minus the initial, and that's equal to negative 0.700 degrees Celsius. There's a parameter called the specific heat, which I'll get more into in a second. And the specific heat of the body, that's what the B stands for there, is equal to 3480, and it's in units of joules divided by kilograms times Kelvin. We are also told that at body temperature, which happens to be about 37.0 degrees Celsius, the latent heat of vaporization of water, so that's going to be when we're going through a transition between liquid and gas. That's what evaporation is. You can imagine liquid water in the form of perspiration on your skin. That transitions to water vapor in evaporation. So we're talking about latent heat of vaporization. That is equal to 2.42 times 10 to the 6 joules per kilogram. Okay, so now let's think of our system as the body and the surrounding air. And so if there's perspiration that evaporates from the body into the surrounding air, and we just think of the body and the air as our system, then we have what's called an adiabatic condition where the total change in heat is going to be zero. It's just going to be transferred between different constituents in the system, which is to say the sum of my heats is going to be equal to the body having its temperature change, because that's going to be associated with either a gain or loss in heat. And the way we describe that is we say the mass of the body, the specific heat of the body, and the temperature change of the body. In general, MC delta T is going to be either the heat required to warm something up if delta T is positive, or the heat lost when something cools down if delta T is negative. So the body cooling down is going to give off heat. But what's going to happen is that the heat that's being given off, okay, to cool down, it doesn't come for free. We need to vaporize the perspiration in the liquid form into a vapor. And so we're going to assume the perspiration is water. And so we're going to say mass of the water multiplied by the latent heat of vaporization of the water. That's the heat associated with the water perspiration on the skin vaporizing, evaporating into a gaseous form. These are our two forms of heat transfer. The body's cooling down, but there's also energy required for the vaporization of liquid water into water vapor. So since this is a system that is adiabatic, where there's no net influx or outflux of heat, it's just transferred from one constituent to the other in the system, we can say that the sum of the heats is zero, which allows us to rewrite this equation as the mass of the water times the latent heat of vaporization of the water is equal to negative mass of the body, C of the body, delta T of the body. And now what I'm going to do is I'm going to divide both sides by the latent heat of vaporization of water. You can always, if you do something to one side, as long as you do the same exact thing to the other side in an equation, you're good. And so what happens is that that cancels. And so now you've got this relationship where the mass of the water that was evaporated is equal to the negative of the mass of the body times the specific heat of the body times the change in temperature of the body divided by the latent heat of vaporization of water. And so, because again, this is going from liquid into gas. And so here's the thing. You see that negative sign there? You're like, well, how can the mass of the water be negative? Well, remember, our delta T was negative. So when you put that negative 0.7 in for delta T, it's going to negate the other negative sign. And so you should see here that we can solve now for the mass of the water that had to be evaporated to cool the body by 0.70 Celsius, because MB, we've got that. We could plug that in. Specific heat of the body, we've got that right there. The delta T, that's this right here. And again, that's a negative sign. And then we were also told what the latent heat of vaporization of water is. And so we can plug all those in and solve for the mass of the water. So that was part A. And then there's a part B where it says, so given the mass of the water that had to be evaporated, we want to figure out what volume of water would need to be re-ingested to make up for the water that was lost in the evaporation process to cool the body down. This is going to utilize a important relationship in thermodynamics of density, where the density of water is equal to the mass of water divided by the volume of water. Density is mass divided by volume. And I can rewrite that by multiplying both sides by the volume of water. I can say the volume of water, don't confuse this with velocity, this is a capital V. Volume of water is equal to mass of the water divided by the density of the water. We are told that the density of water is 1,000 kilograms per meter cubed. All right, we can now solve for the volume of the water because this is just the same as this. So all of this stuff you see in green, that equation you have for the mass of the water, that's exactly the same as the mass of the water in blue. And then you're also given the density of the water. So that allows you to determine the volume of the water that you would have to drink to replace the mass of the water necessary to evaporate and cool the body by 0.700 degrees Celsius. So, a recap. When we have a substance, that substance can be in different states. When it's in a given state, if heat is added, the average kinetic energy of the particles of the substance keep increasing, i.e. the temperature increases. But when there's a state transition, the temperature stays the same during the transition. And this goes both ways. You can take a substance, you can heat it up, its temperature rises, then it plateaus as it transitions to the next state. Once the transition is complete, then the temperature will start to rise again before plateauing into the next phase transition. But you can go the other way too. You can imagine a cooling down process where as more and more heat is lost, temperature in a particular state is going down. Then there's a transition where the temperature plateaus. Then the temperature keeps going down, then maybe another plateau. So that's all to say this graph of temperature versus heat up here. And so now in this problem, we have an evaporation. We have liquid water in the form of perspiration on the skin evaporating into water vapor. And that turns out to be a cooling process. That's why we have a negative sign for the degree Celsius.